Hello, everybody. Hello, everybody. It is today a great pleasure for us to welcome you for this talk, for the talk of Professor Carvalho. Before to start, we are going to introduce ourselves. We are two young students, Maxime and Antoine. We are two young PhD students, and we are members of the MTT student chapter. And today it is a great pleasure that we welcome Professor Carvalho for this talk about metrology development for the future wireless technologies. So I'm going to introduce Professor Carvalho before these talks. So Professor Carvalho received the diploma and a doctoral degree in electronics and telecommunication engineering from the University of Aveiro in Portugal in 1995 and 2000 respectively. He is currently a full professor and senior research scientist with the Institute of Telecommunication, University of Aveiro, and I3E fellow. He co-authored intermodulation in a microwave and a wireless circuit, microwave and a wireless measurement techniques, and the wide space communication technologies. He has been a reviewer and an author of over 200 papers in a magazine and a conference. He is associate editor of the I3E Microwave magazine and the Cambridge Wireless Power Transfer Journal, and a former associate editor of the I3E Transaction on the Microwave Theory and Techniques. He is a co-inventor of the 6 patterns. His main research interests include software-defined radio front-end, wireless power transmission, nonlinear distortion analysis in a microwave wireless circuit and a system, and the measurement of a nonlinear phenomena. He has recently been involved in the design of a dedicated radio and a system for newly emerging wireless technologies. Professor Carvalho is the chair of the I3E MTT 20 Technical Committee and the past chair of the I3E Portuguese section and MTT 11, and also belong to the technical committees, MTT 24 and MTT 26. He is also the vice chair of the URSI Commission 8 Metrology Group. He was a recipient of the 1995 University of Aveiro and the Portuguese Engineering Association Prize for the best 1995 student at the University of Aveiro and the 1998 student paper competition of the I3E Microwave Technique Society International Microwave Symposium and the 2000 I3E Measurement Prize. And he will be the future president of the MTT chapter. So it is a great pleasure to have you in Bordeaux today. So the floor is yours.
Thank you very much. And I asked him not to say so many things about me. It's being a professor, it's enough. Okay, thank you very much first for the invitation. So I will stay here during this week in the University of Bordeaux. And I will give 2 talks, and Anthony asked me that the talk for today will be mainly about more educational works and some works that we did on metrology for wireless communications. Despite I continue to work briefly about metrology, my work now has moved to wireless power transmission and backscattering communication. So on Friday, there will be another talk on more focus on research and less focus on the educational aspects. So the name is there, Metrology Development for Future Wireless Technologies. And first I want to briefly show you from where I come from. So I come from Portugal, University of Aveiro, and my research lab is called Telecommunication Institute. We are a very, very small town close to the Atlantic Ocean. And if you like soccer, this is Porto, this is Lisbon. So we are very close to Porto. And we have surf, beaches, and the things that in Portugal we have a lot, which is beach and you can swim, right? And actually, our town, as I said, is quite small. And my university, that you can see a little bit there, started in '74. And actually, I normally say that we were a spin-off of a company, because what happened was that in my town, Portugal Telecom created a laboratory for developing telecommunication devices for Portugal Telecom in the '70s, and they need telecommunication engineers, and there were no telecommunication engineers in Portugal. So they start the university inside the company with a very small course of 20 telecommunication engineers for the first year. And on the second year, they decided, okay, let's build a university. University starts outside the company, and we start as a company. So we were really a spin-off of a company. And why I'm saying this is because most of what we do in the university is very industry application. So we continue to have laboratories in all our classes. So our students really go through hardware development in a certain sense. Well, the telecommunication laboratory actually started in 1993, so we are quite young. And despite this is a national laboratory, so we have poles all around the country, the headquarters is based in Aveiro, so in my university also. And we cover several areas, from wireless technologies, optics and photonics, information and data science, networks and services, and basic science and enabling technologies. Well, my group is called Radio Systems, and we normally at this moment we cover software-defined radio, 5G, 6G technology, power transmission, RFID, and IoT. So part of my group is putting a lot of effort here, and satellite new space communications. And more recently, we start working also briefly on radar technologies for cars, but also mainly in my group for satellites. So synthetic aperture radars, digital altimeters for radars. Well, these are some of the books that I published. So you can have an overview of what we did in the last years. Actually, my PhD was done completely on intermodulation distortion in power amplifiers. And then I moved to other fields. So metrology is one of the things that I will talk today with briefly. And we work in software-defined radio for white space telecommunications. And as I said more recently, we moved to wireless power transmission. And I strongly believe this is a feature in our fields. So let me. Oh, I don't know what happened. Okay. So let me now move to the topic of today, which is metrology, and how can we use different signals to characterize different components. And I will go through all these topics, but let me say what I want to actually talk about today is mainly on a very simple approach, which I believe you all as a students assume that you know. And I want to show you here today that we don't know a lot of things. And most of the time, and this is mainly for microwave engineers, we work with one transistor. And you see these guys from computer science building these huge chips with millions of transistors. And you say, I have one transistor and I don't fully understand it, how I can capture all the essence of one transistor. And the microwave engineers are around the transistor, one single transistor. And so the topic of today is really what is here, is if you have a system component, if you have a radio component, how you do characterization of that radio component. And most of your undergraduate, and I will believe most of your master courses, unless you get a specific course on nonlinear circuits, you use scattering parameters. You go to the lab, you use S parameters, and that's it. So you extract S11, S21, S12, S22, and you say, okay, I have all the characterization of my device. And this is what I want to show today, that this is not really true. And when you start to have more complex systems, you need to excite large possible ranges of the system. If not, you don't capture all the information. We need, mainly for industry, they should not be complex. So they should be very easy to extract, like the scattering parameters. You click on a button and that's it. So how can we actually capture everything? And if you go to nonlinear systems, how can I assure that I'm capturing all the nonlinear behaviors? And by nonlinear, if you go to the literature, what is a nonlinear system? By definition, is a system that is nonlinear. So all systems are, except the linear ones, are nonlinear. So that means that it's a plenitude of devices out there. And in a nonlinear system, if you go for a filter, for instance, a linear filter, or today in the class that I was with the students, you have a stub or you have a power divider. And if you go there, you excite with one tone, with the one sinusoid, and you see the S11. And if you want to do, and if you want to see how it behaves on frequency, how you do it? You go to the lab, you put your VNA, vector network analyzer, you put a sine wave, and you measure the reflection, and you measure the incident wave. And if you want to do another frequency, what VNA does, it changes frequency, and it repeats the measurement. It changes frequency, and it repeats measurements, and so on. So they assume your system is linear. And you can only do this because the system is linear, so it obeys what it's called superposition. If you don't, if your system is non-linear, it does not obey superposition. Worse than that, if you go and if you have a non-linear system, if you, this is the frequency, right? Frequency of a sine wave is a direct. So if you have a non-linear system and if you excite your non-linear system with the sine wave, the output is the sine wave, but also a second harmonic, a third harmonic, a fourth harmonic, and so on and so on, and also a DC component. So your system at the output is much more complex. So the problem is, how can I capture all this information? And if I now assume that if I excite with one tone, one sinusoid, I have 1, 2, 3 harmonics. If I excite my system with another sinusoid, this is omega 1, this is omega 2, you see? You have 1, 2, 3 harmonics. So what happens if I combine these two? Well, if the system is linear, it will be the combination of these two. This is called superposition. But what happens if I combine these two at the input? The output will be like this. Well, no. If you combine with two sinusoids, the output is like this. You can see it on a spectrometer. Power amplifier is the best device that you have for this. So you have omega 1, omega 2, 2 omega 1, 2 omega 2, 3 omega 1, 3 omega 2, and all the combinations. Omega 2 minus omega 1, DC, 2 omega 1 minus omega 2, and so on, so on, so on. So this is really a nonlinear system. And why is this important? Because when we start to measure nonlinear systems, the complexity grows tremendously. It's even worse than that. These are two signals. This signal is a GSM signal. GSM signal has a constant envelope in time domain. And if you look to the spectrum, it's something like this. This is what it's called a CDMA signal. And this is actually the time domain envelope. You see that the amplitude are not constant. And this is the spectrum of that signal. And what happened is that, okay, let's excite my system with two signals. what I show you here, this is a real measurements. I will show you real measurements, not anything that I made up with MATLAB. So it's real measurements. So this is a simple power amplifier. And what I have here is additive white Gaussian noise that I filter them out, you see. So it's an additive Gaussian noise, I filter them out, and this is the spectra that you can see in spectrometers. Then I pick up and I see the output. So the output is like this. So you have a gain, okay, it's an amplifier, and you see nonlinear distortion around. Now I go to the lab, and instead of using additive white Gaussian noise, I use wideband CDMI. Exactly with the same spectra. So the input power, you see, same power, the same spectra. What do you think it's going to happen at the output? It's the same spectrum. So I'm using a spectrometer, I measure the input signal. And if I don't tell you the input signal is different, you don't know because the spectrum is the same. But when you measure it, it's completely different. And so it's not enough to measure spectra, okay? So spectrometer doesn't give you important information. And why is this happening? Exactly because, let me go back. Exactly because of this. Because even if the spectra is equal, the time domain evolution is different. And this is so complex that, so as I said here, similar power spectral density, similar integrated power, completely different spectral growth. Okay? And the question now is, okay, what type of signal should I use to characterize a nonlinear system? One tone, one sinusoid, two tones, two sinusoids, Gaussian noise, multi-sign signals, other type of signals. What type of signal should I use to characterize my system? And so let's start, and I will go through all the signals that we normally use in the lab. If you use a sinusoid, which is amplitude cosine of omega t, what is going to be the output? Fundamental, second harmonic, third harmonic, and so on. Since most of the time we are using, let me go back. Since most of the time we are using a narrowband system, for instance, a radio that has an antenna, you don't see the second and third harmonic because if your radio is 2 gigahertz, you don't see the 4 gigahertz, you don't see the 6 gigahertz. So one tone is completely irrelevant. Doesn't give you any information. It's only one tone, you see? And what you do with one tone, you normally could characterize linear systems. So you change the frequency and you measure the output frequency, amplitude. So you have the amplitude transfer function and you can measure the phase of the output versus the input. So you can measure how the phase changes of that tone, nothing more. And for a nonlinear system, if you increase the power of that tone and you measure the output, you see that the gain of the linear system is constant and then it collapses. And most of the time in a power amplifier, when this gain changes by 1 dB, you call it 1 dB compression point. So it's in all data sheets and it's done with one tone. And you can measure also what it's called AM to PM. What that means, it means that you increase the power and the phase of the output changes. Okay? And you see that the phase of the output will change with input power. And that's it. There is another thing. Well, how can I do this one-tone characterization? You can use a VNA. So you have your device under test here. You excite your signal with a sinusoid. You measure the reflected wave. You measure the incident wave, and you design all these graphs. Right? And if you are able to use a spectrometer, you can measure second harmonic, third harmonic, and so on. And there is a figure of merit that nobody uses now, but it was used several years ago for cable networks called total harmonic distortion. Well, if you like audio, you know what we are talking about. Actually, if you like audio, if you like rock and roll, you like total harmonic distortion because you have a lot of distortion and you love it. But this is really the things that you can do with one tone. So how you measure total harmonic distortion? Generator, device under test, and a spectrometer, and you measure all the harmonics. That's not very difficult. But what happens? Well, what happens is that, as I told you, if you have an antenna or a filter, you only see this excitation. You don't see the harmonics. And more important, you don't see nothing at baseband. So you don't see nothing. You just see that frequency. So you don't know if the system is strong nonlinear, simple nonlinear. What happens with the bandwidth? You don't really have that information. So the second signal, because people are not seeing nothing with one tone, they said, okay, let me try to do with a two-tone. So I will put one tone in the input bandwidth, second tone in the limit of your bandwidth, and let's measure with the two-tone device. So you have a two-tone, and as I said, if you go to a nonlinearity, the best way is to use a polynomial. You put a cosine of omega 1 plus a cosine of omega 2. You put that on a polynomial, and you do the trigonometrics, and you get a lot of combinations. And what you see for a third-order polynomial, you see two tones, intermodulation, baseband, and so on and so on and so on. This baseband is very, I don't know if I have it here. No, I don't have it. So this baseband is very interesting because this is what you can have. Well, now you don't have it so much, but sometimes you can hear when in the past when you have a GSM phone that has 1 watt sent it to the air. If you put it close to a CRT device, you see flickering because you have 1 watt there all the time. And if you put it close to a microphone, you hear the noise also. Now it's less than. But this tiny tone here is very bad for power amplifiers because it's, I will show you later on, is what brings what we call long-term memory effects. And if you want to linearize your power amplifier, if you have a strong concept, if you have a strong, this is my talk on Friday, how to remove batteries out of a strong process. You have a battery there? Yeah, okay, thank you. You can actually, sorry, okay. I can do that like this. Good. Oh, it's not mine, it's this one. Okay, so I will continue with these two tones. Let me see. Okay. Good, thank you. So, and how can I measure this? Well, since the output frequencies are not on the same frequencies as the input, I normally do not use a vector network analyzer. I use a spectrum analyzer. So you can measure, for instance, one tone, intermodulation distortion. And by the way, if you plot it, this is input power. If you plot one tone, you'll get a signal like this, and then it compresses. If you plot intermodulation, it goes up, and then it compresses again. If you extrapolate this line, and if you extrapolate that line, you get a point that is called third-order intercept point. All power amplifiers have that on the data sheet. And why is this point is interesting? Because if you know this point, you can go back, and you can measure the relationship between your signal and intermodulation distortion in all points up to 1 dB compression point. Then don't use it, it doesn't work. On top of that, IP3 is a virtual number. Your amplifier never gets to the IP3. Okay, if it gets to the IP3, probably bored. Well, how do you measure the two tones? You have two generators, combine the signals, and a spectrum analyzer. By the way, if you want to do good measurements, you need to put at the output of this generator a filter and an isolator. I don't know if you know what is an isolator, but an isolator, if you go into this direction, you have 1 dB attenuation. If you go in the other direction, you have 20 to 30 dB attenuation. Why is this important? Because if you don't do that, most of the time, nonlinear systems are worst. Most of the time, the signal comes from here, not there. This power divider is not always 50 ohm. It comes into this oscillator and gets out. So what happens is sometimes you are measuring intermodulation and you are very happy because your amplifier is creating intermodulation and your amplifier is perfectly linear. Who is generating the intermodulation is this generator here because it gets that signal. So if you have an isolator, if you have 1 watt, comes here, goes to the isolator. If you have a 30 dB isolator, the output is 1 milliwatt and it's irrelevant. So you will not create distortion on the second generators. This is something that you have to take care of. And of course, what can I do with a two-tone? Well, you have the second harmonic, third harmonic, but again, if you have an antenna, you don't see it. You excite the baseband. This is good. But you only excited one frequency. And you can have much more baseband there. So, and there is another problem that sometimes I want to measure phase. And to measure phase with the VNA, it's very easy. The input and output are at the same frequency. So you can compare the phases of them. Like if you put in an oscilloscope, the two sinusoids, you can measure the difference between the peaks of the sinusoids and you measure the phase. But when you have intermodulation, you have frequency components at the output that were not at the input. So how you compare? How do you know the phase of the intermodulation? So we can actually measure phase of the intermodulation by actually creating a nonlinear reference here. So you can create a nonlinear reference, normally the diode that generates harmonics, and you compare the phase of that with that reference there. And you can see if the phase is constant or if it changes with frequency. We will not go through this phase issue at this moment. And if you want to characterize all baseband, if you want to see what is happening at low frequency, not at one single frequency, we can do another thing. We can put two-tone, and if you are in the field of digital pre-distortion, this is very good to see if your amplifier presents memory. So we put a two-tone and we do this. We increase the tone separation up and down. And if you do that, you will see the intermodulation goes up and down and you excite the baseband frequency. And why is this important? I'll go back. Why? Let's see, come here. Okay. Why is this important? Is because when you excite this baseband, you'll see that intermodulation that you want it to be like this starts, if you have memory, intermodulation starts to play going up and down. And by going up and down, you cannot linearize it correctly. So that's why we need to capture these baseband components. Okay, I will not go through this. Let me go next. So this is actually, if you use a traditional spectrum analyzer, and if you start to this with frequency, if you use the spectrum analyzer, you'll see this. That is noise. You don't see nothing. So in this situation, you cannot use a spectrum analyzer. You should use what it's called a real-time signal analyzer, which is a device. It's like a spectrum analyzer, but slices your signal into several samples. So what you should start looking is what we call a spectrogram. What is this? The tones vary over time. And if you synchronize correctly the tones with the spectrum analyzer, what you're going to see is the evolution of this intermodulation over time. And then if you do that with the real-time signalizer, you see two tones varying, and you can actually identify these two tones over time correctly. But even though, as I said, each time you measure the two-tone, you only see one baseband. So what I want to do now is I want to use multiple signs. So instead of using 2 tones, I want to use 10 tones, 100 tones, 1,000 tones. And imagine if I put 1,000 tones into a polynomial, you'll have all the combinations possible, right? So if I put one multi-sign into the signal, I will have a lot of combinations here, second harmonic, third harmonic, and a lot of combinations at DC. So you'll have a multitude of signals. And this is your input signal, this is your output spectrum, and with the multi-sign you can start measuring other things, like adjacent channel power ratio, or what is called noise power ratio. This is very, very important for 5G, 6G power amplifiers. Why? Because in GSM, the bandwidth was 200 kilohertz. In 3G, 4G, the bandwidth goes up to 5 megahertz. In 4G, it can go to 25 megahertz. In 5G, it can go to 1 gigahertz. 1 gigahertz in baseband is from DC up to 1 gigahertz. So anything that happens from DC to 1 gigahertz can impact your 5G power amplifier. Even if your power amplifier is working at 28 gigahertz. If it has a 1 gigahertz bandwidth, that bandwidth is going to appear at baseband with the nonlinear process. So it's very, very important to actually start to look very carefully to the adjacent channel power ratio and to the noise power ratio. So I think I have it here. So for noise power ratio or adjacent channel power ratio, what we do, we have a generator, we have a device under test, we excite the input signal with a multi-sign, which is nothing more than a summation of signs, and we go and we measure the spectra at the output. And the problem with the multi-sign, it's very complex. Why? Because if you go to a lab and you start to add signs, if the phase of each sign is random, the signal, the time domain signal, if you pick up an oscilloscope, will be like this. If you synchronize all the signs, so that means they are all phases, all zeros at a specific time, the time domain is going to be like this. Here I'm showing you 10 tones, 10 signs, only summation of 10 signs. You can do it in MATLAB. What you see here, the amplitude of this signal with randomized phases goes maximum 3 to 4 volts. They are all synchronized, it goes to 10 volts. Why is this important? Because your power amplifier has a compression. So if you have these peaks, it will destroy this amplifier. It will clip the peaks. Peaks, you will have a lot of distortion. And this is the reason why OFDM is very bad for power amplifiers. What is OFDM? Multiple carriers, multi-signs. And each one of the carriers is modulated. So in certain points, you can have what it's called peak-to-rush power ratio, very high peaks. And this is really why when we start to look to multi-signs or when we start to look to modulated signals, spectrum is not enough. Why? Because a spectrum analyzer, what a spectrum analyzer measures is the power of the signal, not the phase of the signal, right? So when you start to have a modulated signal, phase becomes important. And if you have a summation of signs, you can measure phase. If you don't have, if you have a quadrature amplitude modulation or FDM signal, we have to bring another figure of merit to the loop. So we start to look to what it's called the power spectrum density, and more important than the power spectral density, to the probability of a signal to touch a specific amplitude. So the signal at input, let me show it here, is no longer important to measure the frequency, the bandwidth, the power, but we need to start to measure the probability density function of the input signal, which in most of the devices we don't measure the PDF, we measure the complementary cumulative distribution function. I know it's too much mathematics at this moment, but we want to evaluate what is the statistical distribution of your amplitude over time. And depending on the statistical distribution, your amplifier will give you different results. And this is really what I'm showing you here. A two-tone distribution is like this. This is the probability density function. So this is the distribution of a two-tone. This is a distribution of a Gaussian multi-sign. Gaussian means that the phases of multi-sign are Gaussian, are normal, so follow a Gaussian distribution. And this is the uniform multi-sign. So all these type of signals. And by the way, all these three signals have exactly the same power. All these these two signals have exactly the same spectra, but the distribution is different. And because the distribution is different, your nonlinear system will behave differently. And this is really the challenge. So I will show you what we can do then. So this, you see, in this case, what I have is I excite the power amplifier with the same input power, not the same signal. So this is a two-tone and the intermodulation. And here you can see two signals. The input are exactly the same in the spectroanalyzer, but the statistics are different. And you see here that for the, in this case, is the uniform distribution, we have more distortion than for the Gaussian distribution. We have less distortion. And now I know that we have statistics, so I can separate the signals. Before I could not separate the signals. And even worse than that, let me go in front. If I want to know what is happening in each one of these tones when I have a multisign, this will be responsible for the impedance. Imagine, and I think this is very important. For 5G, you are designing a 26 gigahertz power amplifier. You know everything about RF, and you forgot what you learned about DC. What that means? It means that each one of these combinations will create a different multiplication at baseband. So even if you are working on a power amplifier at 28 gigahertz, your 10 hertz response is important for that. Your 100 hertz response of your amplifier is important for what is going to happen. And the nonlinear distortion will degrade completely your system. So I will not go through this, but here is just to show you that this spectra line has impact on, if they are separated by, imagine, 1 kilohertz, has impact on 1 kilohertz, 2 kilohertz, 3 kilohertz, 4 kilohertz, and so on and so on. So all these short impedances will have an impact on your 28 gigahertz scenario. And this is how you can model this. I will not go through this, and I will pass this. So when measuring these multi-sign signals, we need actually to measure the correlated signal, the uncorrelated signal, and if you don't have memory, you have a very pretty result that you expect. This is what normally your MATLAB code and your ABS or microwave office gives you. In reality, you have a lot of these memories that actually is going to degrade your signal. Why is this important? Because if you have this signal, you can design a pre-distorted, a memory-less pre-distorted that works quite well. If you have something like this, to design a linearizer for your power amplifier is extremely difficult because you have to capture the memory from it. And sometimes I would even, instead of actually measure equal tone separation multisign, I prefer to use non-uniform multisigns that gives you more information because it will excite signals that you don't know. So you actually cite the signals in different periods. I will not go through this, and this is how you can do it. So in order, I'm almost finishing. In order, in conclusions, I can say one tone, it's the excitation from a linear system, but it's completely irrelevant for nonlinear systems. Two-tone starts to give you a feeling of how your nonlinear system behaves. Multi-signs are very important to characterize nonlinear systems, but power or power spectral density and spectra are no longer enough to characterize a multi-sign. You need to bring statistics. If not, you cannot. And then let me show you another thing that is, I was talking about power amplifiers, analog components, input, output. You can go to a VNA spectralizer and you can connect your switches. But now, I'll say 80% of your systems, including, I don't know where is my phone, including the phone, is no longer a power amplifier. It's what we call a software-defined radio. It's no longer an analog device. In most of the times, let me go, I have another, okay. I have an image here. Yeah, okay. Yeah, I can be here. Okay, 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 okay. I give you here some examples. So most of the times, these ships are integrated. So in the past, when we talk about software-defined radio, you buy an FPGA, you will buy a power amplifier, you buy an ADC, and you build a system. Now you have a ship, right? And the problem is, okay, how am I going to characterize this ship on the lab? If I go to the lab, I go to a VNA and I switch the input to the antenna, and the output is digital, it's a bits. How can I do that? So again, I don't have time. I told you I have 130 slides. I can share this with you, but I will not go through them all. But I want to show you that actually the same thing I told you about one tone, two tone, multi-sign, we can extrapolate now that for including also a digital component. And it brings another layer of complexity. It's no longer to look to the signals at input, but we want to look to the digital components, digital evaluation at the output. So I will go fast here. I just want to show you that we, in the lab, we actually proposed, in collaboration with National Instrument, we proposed a new instrument called the Mixed Signal Network Analyzer. That actually one port is analog, so you measure the incident and reflected wave, like a scattering parameter. But the other port is digital, so it's a buzz of bits. And we come up with an idea, where it is, I will go, yeah. And we come up with an idea of what we call, yeah, it's here, what we call the D parameters. What are the D parameters? Are the scattering parameters, but applied to digital and analog ports. So they are the digital parameters. Why is this important? Because you can capture also the ADC behavior and the DAC behavior of your software-defined radio, which before you don't care because you have an analog component. Now I don't have analog components. I have mixed components. So we need to actually characterize both of these components. So everything I tell you about one tone, two tone, multi-sign, you can apply to ADCs and DACs and software-defined radio and build a more complex structure. And what is the objective, the ultimate goal? To have a very good mathematical model that you can import in ADS, Microwave Office, CST, HFSS, and do the simulation in the lab and actually identify them. So I will not go through the remaining number of slides. I just want to tell you that on Friday I'll give another talk on more research-oriented devices. Today was mainly to see how can we characterize nonlinear systems. So thank you very much for listening.
Very interesting talks. If someone has a question, we have 10, 20 minutes if you have questions. And online too, you can ask, you can write your question and we will read if you have question for Professor.
I have a question. This type of measurement method, the multi-sign, could be applied to another device as power amplifier.
Yes, yes. I said, can you show the slides again? I said I have more slides. I'll move this. So this is the calibration approach. I will not go through this. Okay. And I will give you an example of something that we are working on, BATERY-LESS wireless power transmission. I think I have it here. Yeah, I can do this if you want. Okay, here you can see it. So this is a traditional, what we call RF to DC converter. So it's a diode, rectifier. And what you see here is that exciting this diode with a single sinusoid, you don't see nothing, because you excite and you create a DC. And this DC, it's, as you see here, this is our real measurements. This is the frequency variation of the sine wave. This is the input power of the sine wave. By doing a two-tone, we immediately start to see that something is happening there. You see? So if instead of exciting my RF to DC converter with a two-tone, if I excite with two tones, I see some changes because there will be a baseband that will interact with your diode. So for certain frequency separations, there will be a dip in the power. And I don't know if I have here, no, I don't have here, let me see if I don't have it. Or, no, unfortunately I don't have it, but I will show it on Friday. So if you excite your RF to DC converter, or in this case, this is a multiplier used in RFID tags. If you excite with a multi-sign, again, if they are all synchronized, you will increase your efficiency of your RF to DC converter if they are randomly. So what that means? It means that if I characterize my RF to DC converter with one tone, or if I characterize my RF to DC converter with a multi-sign, with a more complex signal, you'll get more information for that. So multi-signs is not only for power amplifiers, it's also for RF to DC converters, it's also for ADCs and DACs, it's also for other type of components that you can figure out. And if you look to the telecommunication area, most of the signals now are FDM based. So they are multi-signs. And each sign is modulated. So depending on the type of modulation that you put there, your peak to average power ratio will change. And that is very important. So what that means, it means that all my systems should be characterized with, I will not say multi-sign, but at least a more complex signal. Yes.
Thank you very much. Just one question about digital presentation and
yes.
PA models. We talk about polynomial models, and for instance, it's sometimes narrow model. Do you know inputs or just ideas to mix or to link some some narrow models to get wide model in order to wideband digital presentation?
Yeah, I understand what you're saying. So I've not worked with digital precission in recent years. My knowledge of that is quite old. But nevertheless, what I can say is that if you have narrowband models and if you want to do a wideband model for a nonlinear system, you will have errors all the time because again, a nonlinear system does not obey superposition. So if you do it individually and then you combine it, there will be errors. I believe that if your nonlinear device is memoryless, you can do it. Actually, it's easy to do because in principle, the memory aspect comes more in favor when you have a huge bandwidth. For instance, when I show you the baseband component, if you have narrowband models, imagine that you have 1 megahertz models, and if you want to characterize a 10 megahertz bandwidth amplifier. So if you have 1 megahertz model, this 1 megahertz signal will only generate spectra up to 1 megahertz baseband. So you will never excite from 1 megahertz to 10 megahertz. When you have a 10 megahertz bandwidth, you will excite everything from baseband up to 10 megahertz. So if your power amplifier contains a lot of memory, I don't believe the 1 megahertz models will capture the memory effects up to 10 megahertz. So you'll have to do a 10 megahertz characterization if you want to capture all the baseband or the long-term memory effects up to 10 megahertz. Yes?
And you understand what we call memory aspects for nonlinear system?
Yeah. You see, here you can see Here you can see it. When I excite my signal, okay, here you can see. So if I excite my signal with a modulated signal, it should be like this. A nonlinear system will create all possible new signals. And we'll create a second harmonic, a third harmonic, and baseband. You see. So this baseband is really from DC up to the bandwidth of your signal. So if your signal is 200 kilohertz, this baseband goes up to 200 kilohertz. If your signal is 10 megahertz, this baseband signal goes to 10 megahertz. And these signals will excite the capacitors, inductors that you have in the memory component that you have in your device, in your circuit. So what happens is that if your signal that you are exciting your system is narrowband, you will excite only your system up to this narrowband. If your signal is wideband, it will excite more excitation in the baseband. And this is what I call long-term memory effects, because it will excite the low-frequency component of your devices. And these low-frequency components are not only inductors and capacitors, can be thermal effects, can be trapping effects in gallium nitride device, so can be other type of effects that you don't see if you don't excite a huge bandwidth in low-frequency. No more questions?
Okay. Thank you.
Thank you very much. And don't miss the Friday talk.
And we can have a drink outside of the